And the main question, why FloEFD is so robust, accurate, and easy to use? It's a matter of fact. I listen here a set of presentations, and we see that for a lot of application examples, number of cells are rather less than for traditional CFD. For calculation of spacecraft safety system, it's a very serious thing. If this safety system will not work, cosmonauts and astronauts will be unable to return back, and it will be an announcement on all TVs and etc. For such calculations, FloEFD needs 10 times less number of cells. Due to this technology, we are really able to come to front-loading CFD. We are really able to move our fluid flow modeling to the early stage of the design processes. But how and why it's happened? For instance, yesterday, you remember at evening we seen some strange things, and a good question, how it's happened? Of course, we can say it's magic. It's not magic. It's simply the result of high qualification, of well preparation, and excellent skills. And here, let's see what we are able to do with FloEFD and how it works. We know that FloEFD is CAD embedded, but essential to note that it's not related for any CAD system you are using. It can be a standalone inside SolidWorks, Crea, CATIA, NX, and now even Solid Edge. The technology is absolutely the same. We have one own technology platform, and what you achieve in different CAD systems have to be the same. Equations. Again, we are using the standard Navier-Stokes equations with chi-epsilon turbulence model. We'll tell about this later. But again, the equations are the same. And for any CFD code, the equations are the same. Where is the difference and what is the issue? Why traditional CFD cannot be fully CAD integrated? Why we have an issues with mesh generation? And why it's not so easy to make it robust, and why we need to spend a lot of time for selection of correct turbulence models. The key element is a boundary layer. We are facing with a lot of physical phenomena. For instance, stress analysis, optics, electromagnetics, and a lot of others. But turbulence and boundary layer exists in fluid dynamics. And this is an issue. For instance, let's consider the plate. And the velocity is something like 5 meters per second, and the plate is, the length is 1 meter. The thickness of the boundary layer at the end of this plate, it will be only 8 millimeters. In the middle, it will be even less. Small value, but all physical phenomena which are responsible for shear stresses, for heat fluxes, are exactly in this boundary layer. And if you will have significant mistake in calculation of parameters of boundary layer, then you will achieve nothing. And then it starts. For good resolution of boundary layer, you need a good mesh, good computational grid. If the geometry is complicated, the process becomes more and more complicated. Is it possible to have some workaround? Of course, yes. And promptly, I didn't remember how long it was ago, 100 years plus minus, he developed so-called theory of boundary layer, which based on two main ideas. One idea is that pressure gradient across among the boundary layer it's negligible, and another that gradients across the boundary layer, it's rather less than gradients along the boundary layer. And this idea exists, and this idea was transferred for a lot of interesting analytical or semi-analytical methods of boundary layer. Indeed, the classical approach prefers to work with the direct resolution of the boundary layer. Each approach has pluses and minuses. What is the plus of the classical CFD approach? Firstly, computational algorithm is the same for the flow and for the boundary layer. The physical models, how they are applied, they are also the same. It's very good for computational procedure. What is the disadvantages? The first disadvantage, that it needs a lot of resources. You have to pay for this. And the second disadvantage, you need to be very careful with the selection of the turbulence model. Why? In the core flow, the flow is mainly, it's not uniform, it's not isotropic, but it's not so changing, it's not so have some dedicated directions and etc. Respect the boundary layer. Boundary layer is a flow of very high gradients. And for different situations, different phenomena, some turbulent models which are working perfectly in the core flow will be not perfectly worked in the boundary layer. And even less, for different situations, we can use different turbulence models, or we have to use some advanced turbulence models which are more universal but requires unbelievable computational resources. What is the FloEFD approach? What is the main idea? We calculate the flow field by one algorithm and boundary layer by another one. So the advantage is easy. We are saving computational resources. We do not need a lot of boundary layers in the, or a lot of turbulent models in the boundary layer, because we can take the best from all of this variety of turbulent models and put via analytical methods inside our boundary layer theory. But of course, there is, and then we save computational resources, then we made it fully automatic, then we also will be able to use the rectangular grids. But of course, we have disadvantages. We have two methods, and implementation of more and more sophisticated models will take us more resources. Indeed, we decided to go to this way. And I can tell you some historical background. I will not open you a top secret. The same approach was used for calculations of rocket engines, nozzle flows, and external aerodynamics heat transfer tasks in Soviet rocket and space industry many decades ago. We had the same tasks like Americans, but we have had rather less computer resources, and we were simply unable to resolve it via full resolution of the boundary layer. But in fact, we had the same accuracy criteria and absolutely the same requirements. For instance, when we calculated the thrust in the rocket engine nozzle, the error of the definition of specific impulse was acceptable level of error was 0.1%. 0.2% in specific impulse for the rocket engine nozzle. The price of this was one additional cosmonaut on the spacecraft, because you know the rocket is a very huge device, and at the top the small capsule, like it was shown on the presentation, where 2 or 3 persons are sitting together, and the accuracy have to be very high, and exactly the same methodology were developed. There was a second requirement. When such devices are working, there were different modes with different Mach numbers, with different pressure drops, and with different Reynolds numbers. The engines can be very small and very big. You know that for the main rocket you have a big engine with few meters of diameter, but for small engines they can be very small. Expansion ratio have to be very different. Therefore, there was the requirement to develop the integral model for the boundary layer, which will work in a wide variety of the parameters like Reynolds number, like Mach number, like gradient of pressure, and etc., and etc., etc. And this job was done. Of course, we were unable to use it, but since we know that it was possible, we did this job again. And few time ago, I calculated how many resources we spent for the boundary layer model for FloEFD. It was more than 50 man-years, because we carefully validated in wide range of Reynolds number, pressure gradients, roughnesses, and a lot of other parameters. It was not easy job, and by the way, it was very expensive development. And it was not 1 year development, it was not 2 year development. By the way, the same story was happened with the rectangular grid. Also, the basics technology was approximately 50 man-years, so 50 man-years for the rectangular grid and 50 man-years for the boundary layer. So in a total, 100 man-years. It's only for the basic things without any additional physical models. And what we have as a result after spending of these 100 man-years, we have a technology. Many thanks for our marketing. They give the technology a nice name, Smart Cells. And I like the Smart Cells name, and I will tell you why we are calling this Smart Cells, which works directly with CFD models, which can resolve any complex geometrical configuration, which have very reliable and automatic meshing algorithms. And we do not require any specific qualification to define these grid parameters. So firstly, a few words about the grid. It's usual rectangular grid, where one cell can intersect the body into the arbitrary way. Principally, nothing outstanding, nothing complex, and each cell, when we adapt it to the floor, to the solid boundary or to the floor field singularity, can be refined. Principally, it's possible to achieve not only by FloEFD, but again, this is only one part of technology. And without boundary layer, in my opinion, it's not fully useless toy, but it's not efficient toy. So, of course, we have a lot of possibilities how manage with this mesh in automatical way, a lot of criteria. As for geometry, as for the flow field, I don't want to spend your time. We have a set of solvers. Some solvers, and maybe in 95% of your applications, you use our classical base fully implicit solver, which is valid for subsonic or transonic and supersonic calculations with Mach number not more than 2.53. It depends from situations, but in absolutely majority of your applications it's okay. For applications with high Mach number, more than 3, we have a special explicit solver which is working perfectly up to Mach number 30. Why 30? Because Mach number 30 is exactly the Mach number when somebody is returning from space. More than 30 usually not exists. And we have a special hybrid solver for cavitation. It's an interesting long story. I will not fully touch it during this presentation. But in this solver, we really combine all our experience from our fully subsonic and supersonic flows, because in cavitation zone, the sound speed can be very small, 10 meters per second, even less. And the flows, in fact, behaves like fully supersonic flows. And we put it together and create the hybrid solver. But in fact, a lot of CFD codes have different solver. What is really unique in our software is the boundary layer treatment. And we have two basic approaches, so-called thin boundary layer, where the thickness of the boundary layer is comparable with the size of the cell or less, and thick boundary layer, where the thickness of the boundary layer is more than 10 cells. So in first case, we use so-called thin boundary layer. In this situation, we are using classical wall function, and in between we have some intermediate models. So this is for what we spent the second 50 man years. So the first 50 man years we spent for the grid, the second for this boundary layer. But only combination will work. Each element separatively, of course, gives some benefits, but in combination we achieve what people was shown. For instance, they calculate via classical CFD and via FloEFD give the similar results, but the resources, the differences resources can be 3, 4, 5, 6 times, or even 1 order of magnitude. Thin boundary layer, it's mainly based on this Brandt theory. So we made some assumption regarding boundary layer, and the main assumption that the direction of the vector of stress tension of the wall is parallel to the external velocity. Principally, it's not happened everywhere. There are some interesting flow phenomena where the boundary layer is fully three-dimensional. And of course, here such method will give some error, but maybe in 99% of applications it's the same. But again, if you will met exactly this situation, put more and more cells, you will come back to the classical CFD and you will achieve the result. Essential to know that after that, having this simplification, having this hypothesis, we create the integral methods for the boundary layer. These integral methods became grid independent, and then we are able to operate with this. With thick boundary layer, we are using something intermediate between traditional wall function and what we are using in thin boundary layer, and again it works. But this is not the whole picture. One additional benefit we understood later when we already became CFD integrated and when our product already was in commercial use. Since we are working with the native CFD geometry, really native, we do not have some intermediate format, some intermediate files. We have the full access to the CFD model. And we know Sometimes it's a pipe. Sometimes it's a space between two planar plates, or it's some dedicated physical configuration. This information we obtain directly from CFD model. And since we have this information, we can recognize that within your huge computational model, you have a pipe or a set of pipes. And since we know the velocity, the density, other parameters, we can calculate Reynolds numbers. And if we see that the number of cells is not enough for the full resolution, we can come into analytical solutions. And again, we can do it in a fully automatic way. And then we understood it's also a big advantage for our technology that for some dedicated situations, which can happen, and for instance, for some heat exchangers, for selections of pipes, or with some heat sinks, it's happened very often. We can substitute by analytical solutions our 3D solutions. And we are using this. So we have rectangular grid, we have our boundary method, which is in fact also combination with analytical solutions. We have in some dedicated cases, analytical solution which is fully automatic. And then we understood it's more than rectangular mesh, it's more than simply analytical solutions, and we come to this nice name, smart cells. So these cells are really understood where they are, what is the Reynolds number, what is the thickness of the boundary layer, are we inside or outside some analytical solutions, and manage the situation. This is why I like this name. And this allows us to save the resources. This allows us to use rectangular grids, which are very easy to make fully automatic grid generation. Of course, it's very essential to talk with CFD specialists, because at the beginning they cannot understand how you achieve the high accuracy. It's necessary to mention on this phenomena. I will not show you a lot of validations. By the way, for each release, for each service pack, we have a battery more than 400, it's 400 test examples, which covers a wide variety of different tasks for different applications. And if any task is not working, then we need to find and to recognize why it's happened. So it's really fully validated, and principally here there are a lot of presentations from your side showing the high accuracy of this approach. And I just show you two examples. It's one example showing the usage of these analytical methods for dedicated cases like flows between two planes, and you can see the grid, the number of cells from the point of view of classical CFD is not enough. And here there are two cases are presented. In one case, the number of cells for such model, it's about 4,000, so it's full engineering methods are working. In the second case, the grid is close for what are using in traditional CFD. It's 400,000 of cells. Experimental data is present, and you see that the difference with experimental data is the same order of magnitude. Sometimes engineering method is better, sometimes full resolution is better, but again the difference is few percentage. Here it's the example of heat exchanger with a long pipe, and there are three kinds of grid with absolutely different grid resolution. In first case it's 200,000 cells, in second it's more than 500,000, in the third it's approximately 1 million, but the results are practically the same. It's really interesting fact. Sometimes it's even confuse a little bit the user, because for traditional CFD, the more cells you have, the accuracy increase monotonously. For us, it's not exactly the case. Of course, if you will have a really big number of cells, it will be monotonous. But at the beginning, where engineering model is working and we are moving to classical CFD, it's not monotonous. Okay, what else? Oh my God. People ask us all the time, why you have only one turbulence model? Why you have only K-epsilon model? The answer is not that we are lazy. The answer is not that we had no experience with other CFD models. By the way, it was 21 years ago, before we started the first CFD integration, we had 7 turbulence models in our code, already at that moment. And in principle, we were able to move it into FloEFD. But what we understood, maybe we are not lazy, maybe we are lazy, it's a good question. I think we are not lazy. But definitely, our users also not lazy, but they have a lot of other tasks if we are talking about front-loading CFD. And for them, often, our tool is a supplementary tool. If we will ask them to think what turbulence models they have to use, forget about use it in early design stage. They will spend a lot of time for this. But in fact, the correct answer is we have one turbulence model in the core flow, and what we have in the boundary layer, it's a combination of a wide variety of turbulence model which were transferred into analytical or semi-analytical approach. In fact, it's not a K-epsilon model. It's very far enough. Also interesting that I think it was about 10 years ago, after a lot of pressure, after appearance of SST model of turbulence, we made a wide study with K-omega turbulence model, with SST turbulence model. We implemented into our code and made a lot of calculation. So we hired 2 very nice interns, which did all this. It's not fully monkey job, but dirty job. 2 our gurus sit and check what these 2 interns did. By the way, one of these interns obtained PhD and then moved to Italy, and I hope he will be a very famous professor. The second is working in another field and achieved a lot. We spent a lot of time of our CFD gurus. The results was practically the same. And then it was already in our graphical user interface, but then we decided to stop this experience because it gives nothing to our customers. We keep it as it is. At the moment, sometimes we come to very stupid ideas. If somebody of you, maybe not you, or other customer wants, we will implement maybe 10 or 15 turbulence model. We will call it advanced C++ or advanced++ model. We will establish the price something like 20,000 USD. And somebody who wants to take it can take it. As I told, after this lunch, my shape is not ideal. And for me, it's better to decrease it a little bit. But principally, if I want, I can come again to restaurant and had the second lunch. It's not forbidden. I can even pay for this, and maybe my company will approve it. Alexander, but
you know, FloEFD eats it all.
Yeah, and but will be it healthy or useful? It's a good question. The same with the turbulent model. We optimize our software not for doing PhDs, not for doing deeply research work. We optimized our software for solution of practical tasks in prescribed time and with a high accuracy. And at least at the moment, for more than 90% of the cases, this approach is enough. And if something which has happened will not satisfy you, please come to us, and we will see what to do with this. And as I told, I will not tell a lot about some validations, applications. Principally, you already our best validation base. I just show you only one example. It was done by Japanese Society of Automotive Engineers. They consider two models of the car. One was without the screen, the second was with the screen, and it was in the nice wind tunnel where there were a lot of measurements. I will not show you all results. I will show you integral parameters which were done by different CFD codes. And among this variety of CFD codes, there are some codes which you know very well. We put it by this, like star SSM plus or SKU-tetra. SKU-tetra is very popular in Japan. This is why they note about this. FloEFD, of course, here there was ANSYS. And there are, these slides are two lights for two cases with the screen and without screen. This is for the drag coefficient. This is for the lift coefficient. And you see that FloEFD is inside the best results. But what is essential to know that alternative codes used different turbulence models, and even different turbulence models for different calculations. For instance, for drag coefficient, it's again for lift force or for pitch moment. So the user select what turbulence model did. We did the same approach, chi-epsilon model in the core flow, and our semi-analytical approach in a boundary layer, which in fact a combination of a lot of turbulence model. And then it was the winners for each case, for drag coefficient, for lift, for pitch moment. And FloEFD is only one code which is inside winners for each task. But what is essential, it's only one code which use one approach. So this is a code best for the practical usage. So maybe I can continue more and more, but I would like to give you a possibility to ask questions.